So today we're going to start with chapter 5, functions of random variables. Alright, so this is a very useful chapter because there's typical questions in engineering that ask questions about functions of a random variable that we may know. So equation 5.1 here represents the general problem that we're going to be studying. Okay, so there's a function g of x, y equals g of x, and we know the distribution of x. So we know the PDF or the PMF. Okay, and the question is, what is the distribution of y? Right? So many examples come to mind. If x is the wind speed, for example, then you're interested in the force that wind speed would generate in your structures. So g would be the function that translate that wind force to the force upon the building. Right? So there's infinitely many engineering applications under this category. Okay? Okay, so the question that we'll be asking in section 5.1 is, what is the distribution of x? Now, let's get this out of the way right here. Many times, the only questions you want about y, it's what's the mean and the variance. Okay, so for that, you do not need to know the distribution of y. We can just apply the expected value of a function, as in here. Right? So in those cases, you can do without the distribution of y. Alright? Okay, so this procedure is when the question is, what is the distribution of y? Alright. Now, let's get another concept out of the way, which is really important in engineering. It is this notion of the naive approach and the correct approach when approximating functions. Okay. So this remark right here says it all. Okay. So let's say you want the expected value of y. Alright. Now, the correct thing to do is to take the expected value of g of x. Because y is g of x, right? Yes. But what most people like to do is this last equality here, which is evaluating g at the expected value of x. Now, the difference is kind of minimal, right? It's e of g here, and then this is g of e, right? But that's the whole difference. And conceptually, it means, for example, e of g of x means that you're going to take all the values of g of x and take the average, so to speak. Right? Because expected value and average are similar. Alright? So you have to evaluate that function g of x, hopefully at all sample points of x, which might be a lot. Right? So it takes computation time or your own time. So it's a long computation time, let's say. However, this last equality here, g of e of x, is just one computation. It's evaluating the function at one value, at the expected value of x. Right, so it's a lot faster, but in general, it's not going to give you the right answer. The only way it's going to give you the right answer if g is linear. That's the only exception. So when you have linear functions, then you can say e of g of x equals g of e of x. But in general, that's not true, right? So we're going to call this the naive approach or the lazy approach, right? When you just evaluate the function at one point, and that point is the mean of x. And remember, the correct approach is evaluate that function many times and then take the average. All right. So let's get started with an example we already saw just to illustrate what we're going to do. We're going to start with a discrete distribution. So the PMF of x is known, it's right here, and we're interested in the PMF of y, which is x squared. All right? So we can do it by just looking up what are the possible values of y, right? And you soon find out that, so if you square these terms, right, you're going to get only two values for y equals 0 or y equals 1. Okay? And so with, for example, here the probability y equals 0 is the probability x squared equals 0. That means that x has to be 0, and this one we know from the PMF, right? So we're translating probabilities from y to probabilities from x via the function x squared in this case. Similarly for 1, right? So that's x squared, and then here we solve for this equation, x squared equals 1. So in this case it has two roots. We're going to call them, this is going to be x1 star, so the star would mean root. That's the first root. The second root of this equation, we're going to call it x2 star. Okay? But this is kind of what we're going to do for discrete distributions, and then we're going to stand it for continuous distributions. Okay, so this is a continuous example. So x is uniform, so that's the PDF, and we want the distribution of e to the x. Okay, so here we could start just by asking the question, what is the CDF of y? So probability y less than little y. Definition of y right here. Then here we're taking the inverse, right, to go from here to here. That's important for you to note. Right? Because we're taking the log in both sides, right? So that's like taking the inverse to get the function x as y as function of x, like here. And then this is, by definition, is the CDF of x evaluated at log of y, right? So this guy is the inverse of this function, and it happens at this step right here. Okay, so the notion of inverse will be really important in our discussions. Okay, and then once you have this, so you're kind of done, right? Because just evaluate for the CDF, right? So here we're saying it's the integral of the PDF, so it's log of y in this case for the uniform distribution, right? So in general, once you're here, you can take derivatives, and then you would obtain the CDF of y, right? So this is what we're going to do. These are kind of the procedures that you would do by hand, but now we're going to present formulas that you can apply to any problem. And in that way, we'll be able to generalize it to more functions. Okay, so let's start with a single discrete random variable. All right, so what we saw before is that we need to solve that equation, right, to get the roots, and that's the g minus 1 of y. That's the inverse function. Now we're going to show you several pictures to get an intuition for these formulas, but this is going to be the recipe. All right. So let's start with this example. So the picture is a little confusing. You have two axes, the blue one and the black ones, right? So the blue one just shows you the function. In this case, g of x would be 1 minus e to the, all right? It's a nonlinear function like that. Okay, and the black axis, so first this one down here, it's obviously the PMF of x, right? And this one is the PMF of y. And this is the probabilities, right? These black dots. So we see that x has a uniform distribution, right? Because all the the probabilities are identical. And the sample space are the points x1 through x5. Okay, in red we have the expected value of x. Okay, all right, so the variable y, which is a function of x, all right, and that's the shape of it. All right, so for each xi, there will be a corresponding value of y. Those are all the yi's, right? So, yeah, obviously the yi's are simply the function g evaluated at the xi, right? All right. And this is really what happens. That's all we need to know about discrete random variables. We just follow the lines, see what the new values of yi are, and then apply the same probability, right? So this height right here is the same as this height right here. Now, these are all the same height, so it's going to be true for all of them. But if they were different, like this height right here for x5 is the same as this one right here, right? It makes sense because what we're saying here is that if you want y equal to y5, for example, right here, then you need, so the event that y equals yi is exactly the same as the event that x equals xi. That's kind of the basic idea in this chapter. And it's by definition, right? Because if you want to have the value yi, then the only way to get that if x equals the corresponding xi. Okay? All right, so really that's the main ingredient here. Because then what we do here is we're going to express now the x's as a function of y with the inverse function g to the minus 1, right? So it's kind of the inverse of this one. Okay, in this case it's the logarithm function. So once you have the inverse, you can say, right, we replace this xi right here by the inverse. Right here. And that's the recipe, really. Okay, this is the recipe. The recipe is evaluate the PMF of x at the inverse of y. And that's it. That's it. And that is saying that the probability of y equals yi is the same as the probability of the corresponding x. That's it. Nothing else. Okay. So, in this case, the function is concave, right? So, for concave functions, we're going to have this. Which this type of equalities are called Jensen's inequalities. I'm going to write them in a minute. Alright, and this is from the figure, look. And this is the naive approach versus the exact approach. Alright, so E of g of x, it's E of y, right? Because y is g of x. So this is the right value of the green one. That's the correct expected value of y. Now, if we evaluate the function at E of x, alright, so we would have to go up here and then to the left, right? You would find that right over here is the function evaluated at E of x, right? And you see, by comparing the blue dot and the green dot, that the blue dot is greater than the green dot, right? So what's happening is that the naive approach, the lazy approach, overestimates the mean. All right? Okay, and we're going to see ways of improving this approximation, making these two expected values closer together. But anyway, remember that whenever the function is concave, then if you use the lazy approach, you would be overestimating the real mean of y. All right, let's look at a convex function like here. So it's the same uniform distribution for x, right? These are all at the same height. And then the function g changes, right? And yeah, needless to say, this is g of x, which is 1 over x in this case. Great. So same thing. This should be all the same, except that the inverse now is obviously different to 1 over y I. Okay? And the recipe is the same, this one right here. But here is, we have the opposite sign, right? Here, the lazy approach underestimates, right? Because if you go up here and then to the left, then the blue dot is below the green dot, okay? Oh, and by the way, so the E of g of x, the E of y right here, the green dot, is calculated using the regular formula for expected value, right? Because we know the PMF of y is all these values. Okay? Very good. This is yet another example. What's different? Oh, what's different is that x now is kind of Poisson distributed or binomial, right? It's like a bell shape. It's not uniform anymore. Okay, so here, the same story, right? So, for example, for y8, which correspond to x8 right here, right? So what we're saying is that the height of that probability should be the same as the one for y8. No, y7. There's a problem with the numbering. Yeah. No, so it corresponds to this one, right? Because if you follow this line, you end up here. So this height right here has to be the same as this one right here, which is true according to the figure, right? And again, that's the idea, is that probability of y of yi is the same as the probability of the corresponding value of x, which is going to be the inverse of the value of y. Okay, so the heights are all the same, but the location of the points is different, right? So the shape of the distribution of y differs from the one of x. Okay, and finally, if the function g of x is linear, as in here, everything's the same, right? Again, we have the same heights and everything, and E of x, the lazy approach and the right approach are the correct approach. All right, let's look at a case where the solution to the inverse has two roots. All right, so here we have a parabola, and x has the uniform distribution all along the x-axis here, right? Okay, and then the distribution of y, it's like on a 3D axis right here, hopefully, okay? Because we need to show too many things in this graph. Okay, so what happens is, for example, the probability of y equals y2, it's from the figure, is the probability that x equals, right, this value, x2, but also plus the probability that it's equal to x6 in this case. And this should be equal here. Okay? that is a concept. When you have more than one root, we just add the probabilities, right? Because the only way, well, there's two ways now. The ways that y is going to be equal to 2 is either if x equals x2 or x equals x6 in this figure. Okay? And x2 and x6 are the solutions to our equation y equals g of x right here. Okay? So, and these are the roots of the equation. In this case, we only have two, x1 star and x2 star. But in general, you can have up to k. And the general strategy is just add up the probabilities of x at all those root points. All right? So for example, here, you put y2 equals g of x, and then that was going to have two solutions, x2 and x6 in the figure. All right? So that's pretty much it. So here in the figure we have just two roots, and then we're going to add them up, one plus the other. Now the point 0 here at the origin, the red one, x for y4, is different because it only has one root, so that one only uses one root, like that. All right, very good. And Jensen's inequality, then here you see that in this case the lazy approach underestimates. So the lazy approach is right here, and the true value is right up here. Okay. So these are Jensen's inequalities, which it's a summary of what we've seen, right? So you need to be careful. Whenever you have nonlinear function g of x, you're going to make an error or a bias. You're going to have a bias in your predictions if you use the lazy approach or naive approach. If it's linear, it doesn't matter. They're all, both are the same. Okay, let's do a quick example for the discrete. So in this case, we have x being binomial, and then we're interested in the function y equals e of x. Okay? All right, so that's the recipe right here. It says simply use the PMF of x evaluated at the inverse function of y. Okay? Now, this is saying that you need to make sure that the inverse function falls in a sample point of x, right? Because it might not. So what that is saying is that, for example, in any of these, right? So if you want to see what's the probability that y equals this value of y, it's 0, right? Because if you take the inverse, you go down here, you end up with this point for x, which is not in the sample space of x. So the probability of y equal this y right here is 0, which is what we're saying in this line, okay? All right. Then, in this case, we compute the inverse function, log of y, and then what we do is wherever, so that's the PMF of x, right? And what we do is wherever we see x, we plug in the inverse. So log of y. So three places. Right? 1, 2, and 3. That's it. Okay? So discrete cases are easy. Here's another one. I'll let you guys do that. Now let's talk about continuous random variables, which are a little bit more involved. Okay, so that's the recipe. Don't worry about it now. We're going to show it in a minute. Okay, so let's focus on the picture on the left, which is the same, right? As before, we have, this is g of x. Now we have the PDF of x in blue here, right? Like a normal distribution. And we have the corresponding or the resulting PDF of y in the gray axis here, right? which would be a log normal looking. Okay, all right. So in this case, the recipe is that, let's say this is x. This is, oh my goodness. That's x right here. And that's the corresponding value of y. Okay. And this distance is going to be dx. And this one is going to be dy. Dx and dy like that. They're going to be related by the function g in that way, okay? All right, so the same recipe that we use for discrete, that is that the value of y, like the height, right? The heights are the same, the probabilities are the same, remember, for y and x. Now, here, when continuous random variables, we're going to say that the areas are the same. So this area right here has to be the same as the one that I'm coloring right now. Right, because that's the probability that y will be close to y, right? Y plus dy. That has to be the same as the probability that x is within x plus dx. Okay? So what we want is to make those two areas equal areas. These two areas equal. Okay? That's the recipe. It's the same as the discrete, but now with the areas under the PDF curve as usual. Okay? All right. Now you see here from the figure that at y, for example, it doesn't matter where, the slope right here is simply g prime. Right? The derivative of g. All right, so from this figure, we get the relationship, right, g prime, obviously, right, the definition of derivative, dy dx. So that's how the dy and dx are related via g prime. Okay, but let's look at this inverted. So I have y here and x right here. Okay, and the reason we want to do this, it's because since we have the inverse, it's going to be more useful to have the derivative in terms of the inverse. So what I'm saying, this is the function g minus 1. So the inverse of g, right? Because we flip the axes. All right? Okay, so in this figure, if I draw a tangent and then the slope, you would see that by the same definition there, that now dx dy is going to be the derivative of this function. So the derivative of g minus 1, and let me write it down like this, ddy of g minus 1. And this is a function of y, right? G minus 1. Okay, so we're actually going to use this formula, which is just the definition of derivative, but using the inverse function, g minus 1. Okay? Now, and this is this equation right here. Now, the absolute value comes in because this picture is true, or this equality is true for g minus 1 here being increasing function. Okay? But when you have a decreasing function, then the derivative is going to be negative, right? It's going to be negative, a negative number. Um, but in this case, so since we want to relate dx, the width of dx and dy via the function up here, right? So dx is a constant times dy, right? And that constant is the derivative at that point, and that has to be positive, right? Because we're relating the sizes of dx and dy, not their direction, so to speak. And that's why we put the absolute value sign. All right? So the absolute value takes care of increasing and decreasing functions. And that's going to be a recipe, right? And yeah, this is the condition that the probabilities are the same. It's the f of y dy, which would be this area right there. And the area right here for x is f of x times dx, right? Which is this one right here. All right. So we put these two together and we obtain the recipe, which is pretty similar to the discrete one. So it says, so the PDF of y is the PDF of x evaluated at the inverse. So that's exactly the one for the discrete. But this time we need to multiply by the absolute value of that derivative. Okay? And yeah, hopefully you can see why we need to do that, because the areas or the sizes of dx and dy right here, they change according to g prime. So the flatter it is, for example, so the function were really flat, you see that the corresponding dx would be a lot larger. So anyway, so that's the intuition, that's the theory, that's the equation that we're gonna apply. All right, and then some figures just to show you how the input PDF of x in this changes according to the shape of g of x. All right, so you start with a uniform and you end up with something that's not uniform at all. All right, this is a normal, that's an exponential function. You would have a log normal distribution for y. Okay, so let's start with this simple example. The function is e of x again, and x is normally distributed. And the question is, what is the PDF of y? All right, so we start with what we know. That's the PDF of x. That's our recipe. Okay, and then we compute the inverse of our function and the derivative of that inverse with respect to y in absolute values. That's 1 over y, okay? And then that's all we need to apply the formula. So we're going to take this PDF of x, and wherever it says x, so only here, we're going to plug in the inverse value, so log of y, right, on that place. And then we're going to multiply by the absolute value, which is y over there. Okay? And you'll see that that is the log normal distribution. So if you compare this PDF with the one for the log normal in chapter 4, you would see that they're the same. So here we're showing that where the log normal comes from. Okay? Very good. Try to lose one is the same concepts, nothing new. This is also the same. This one, let's do this one because there's two roots. Oh, but yeah, this is only defined for the positive x's, right? So this is an example where you have two roots for your equation, but one of the roots, the negative one, it's not in the sample space because it's only for x greater than 0. So you're going to consider only one root in this case because the other is not in the sample space, right? So that's one root plus the other root, but this is negative, so that's going to be 0. So it's actually, you end up with one root. All right, let's talk about two random variables now. This is going to go a bit quicker because it's a direct generalization of the one variable case. Okay. Okay, so here we have a function of two variables. So now the joint PDF of x and y should be known. So in this case, it's the joint PMF. So yeah, it's the joint PMF is known, right? And then there's a function z, g that relates z and the other two. So you want to know what is the PMF of z in this case. All right, so and the general recipe is this one. It's that they're going to consider all the probabilities for xy that kind of at all the inverse points. And one way to get all those is just to say all x and y's such that that equation is true. So all those points, those are the roots of that equation. So that's one way of saying is the sum of all probabilities or at all the roots of this equation. Okay. Now, when we have monotone equations, then it's easier, right? When it's only one root, which is going to be the case for the most part. And we have two options, as you hear. And the option is how we define the inverse, right? Because you could define it in two ways when you have two variables. One is that the inverse be the inverse with this, so that would give you the value of y. So in this case, this would be, y equals, I could say. Or in this case, I could say x equals. And this should be, no, this should be z and y. Well, I guess it doesn't matter. Yeah. Right, so here we are taking the inverse and it gives us y, and the second one, the inverse gives us x. Yeah, so in the first one, we use the inverse for y and the second one for x. Now they're identical, you're going to get the same answers, but there's just two options. All right, let's do an example. Let's see the sum of two Poisson random variables. Okay, so we know the PMF of Poisson, and they're independent. We know the PMF of Poisson, right? Okay, and then we apply the recipe. It says do the sum for all xi's such that they add up to z in this case. Okay, so we're going to take the first approach, I guess, where the inverse gives us y here. Okay, so in this case is z minus x, right? That gives you the value of y. That's what we mean by the inverse in this case. Okay, and since they're independent, the joint PMF, P of xy, is just the product of the marginals, right? And one is evaluated at x, and the other is evaluated at g minus 1, which would be this one. Right, because that's g minus 1 right here. Okay, and from here down is algebra. You're not required to know this. It'd be good, but it's not something that you would lose points from. Okay? Now, what's nice about this algebra is that it shows you that the sum of these two is a Poisson random variable with the sum of their rates. Okay? So now you know why the sum of two Poissons is Poisson. Okay, let's do a continuous case. The continuous case is also similar. So if you notice, this part of the equation is almost the same as the single case one, right? So remember, it was the PDF of x evaluated at the inverse times this absolute value, right? Now what we do is, because we have another random variable, we're going to interpret that result as kind of a joint density of x and y, and then we're going to take the marginal, so we're going to do the integral over the whole, over all values of y. Okay? And again, as in the discrete case, we have two options. That's option 1 or option 2, depending on what inverse we choose to do. Right, so here it gives you the value of x, and here it gives you the value of y. Okay? So again, it's the same formula, but for two variables. So the joint times the absolute value, but then we take the integral, because we're kind of taking the marginal. And that gives you f of z, right? Okay, so let's do some examples applying this equation. So let's do the sum of two exponential random variables. X and y are exponential with different rates, lambda and mu. We know the PMF of each, right? And then we know the joint distribution because they're independent. It's just the product of the two. Okay, then that's the recipe. We're using the first, so this would give you the value of x right here. Okay, and then the absolute value term is z minus y, and then we take the derivative with respect to z, and you're going to get that it's equal to 1, right? Very simple. So, all right. And then, yeah, this is your function that you're going to be integrating right here. So again, that's your recipe, and this is the recipe once we evaluated all the terms as before. All right, and you get this PDF, which doesn't have a special name. All right, and just to remind you guys, so if x and y had the same rate, so lambda equals mu, we would obtain the gamma distribution as expected. All right, so you would have to start all over and integrate this function with lambda equals mu, and then you'd find that you would find that equation, and that corresponds to the gamma distribution. All right, one more. Just to, now let's do the product of two exponential random variables, again with different rates lambda and mu. So it's pretty much as the other one. Yeah, make sure you get these, right? That's the inverse, and that's the derivative of the inverse. We already had the joint PMF, which is this one. So there you have it. Now, in this case, this integral doesn't have an analytical solution, so it has to be evaluated numerically. All right, and then, yeah, we're not going to do this, but this is the sum of two normal distributions. X and y are normal, and then you can show that the sum is going to be normal as well. Yeah, there's a lot of equations to do this one. We could do it in class, maybe. Excellent. All right.